Hello guys, my name is ANKIT JASWAL and I'm doing mechanical engineering from VIT Vellore. And today I'm going to deliver a lecture on optical fiber as my DA1 in engineering physics. Fiber and optical fiber. First of all, you know that it is used in telecommunication and it is the science of transmitting data, voice, images by the passage of light through thin transparent fibers. Okay, and you all know that it has been used in medical science for endoscopies and for in manufacturing processes too. A- and it is used for inspecting interiors of manufactured structural products. Fine. So, light energy can be modeled in three different forms which relate the particular model of light to the context in which it is talked about. Light can be characterized in any one of the following models: ray model, wave model, and quantum model. If I talk about the construction of optical fiber, it is a solid glass rod called core through which the light in the form of optical signal will propagate, and this rod is surrounded by another coaxial cylindrical shell made up of glass of lower refractive index, which is called cladding. Please remember it. So I will show you the more. I will show you the diagram for the illustration of this all theory part. Yeah, you all can see the diagram. They have illustrated in a better manner, and the second diagram also. It is a light ray coming. It is a core, it is a cladding, and it is a coating, plastic coating. Okay, and it is the detailed construction of optical fiber. You are having here core cladding of 125 micrometer, buffer of 250 micrometer, jacket of 900 micrometer. See, the internal reflection is taking place between core and cladding. Okay, you can see the diagram also. So yeah, the diameter of cladding, I have told you that it is 125 micrometer. I have told you entire theory in the diagram also, so you can refer that also. The light energy in the form of optical signal propagate inside the core cladding arrangement and throughout the length of fiber by the phenomena of total internal reflection, as you have studied in your class 12. Okay. So the phenomena occurs only when refractive index of the core is greater than the refractive index of cladding. So cladding is made up of glass of lower refractive index. Fine. So by the phenomena of multiple reflection at core cladding interface, the light propagates throughout the fiber over a very long distance with low attenuation. Please make a note. So there is also a minimum loss of information by transmitting the data through optical fiber to a very long distance. Okay, yeah, you can refer the diagram. It is the diagram for the launching of light into an optical fiber. You can see this diagram. It has so beautifully illustrated you each and everything. So I will explain it in theory too. If a ray is incident on the core of optical fiber from the side, the ray simply refract out of the fiber on the other side. Okay, and the ray shown in figure 3.2 in green demonstrates the situation in more vivid manner or lucid manner. Okay, no matter what the angle of incidence of the light is, any light that enters the fiber from the side does not propagate along the fiber. Okay, the only option that's available with us is to launch the light through the tip of fiber. This is in order to guide the light along the fiber. The light must be incident from the tip of optical fiber, and The red ray of light is exposed to the is in figure the red light in figure 3.2, which explain this situation. In other words, the tip of optical fiber is not exposed to light. No light will enter the fiber. Okay. So although there may be an ambient light, as long as tip is protected, no light from the side propagate along the fiber. Equivalently, if there is propagation of light through the fiber, no light would emerge from the side of the fiber. The characteristic of the optical fiber impart an advantage to information security of optical fiber communication technology. So after going through the entire article or entire concepts, the question might strike your mind. Okay, that whether a whether a partial reflection at core cladding interface is sufficient is suffices it will suffices the propagation of light along the fiber over long distance or not. Then the simple answer, no, no, it won't. The reason is that each reflection at a part of the optical energy is launched into the optical fiber would be lost, and after certain distance along the length of fiber, the optical power would be negligibly low to be of any use. Thus, total internal reflection is absolute necessity at each reflection for sustained propagation of optical energy over a long distance of fiber. So the sole reason of launching light into the fiber at particular angle so that light energy propagate along the fiber by multiple total internal reflections at core cladding interface. Fine. You can see you have studied the Snell law. It has been also illustrated in the diagram. Okay. Here N1 is the rarer medium of refracting index N1 and N2 of refractive index, which is a refractive index of medium 2, which is your denser medium. So let us discuss the rules and the laws. So the angle measured in the expression for Snell law are measured with respect to the normal angle to the media interface at some point of incidence. If N2 is greater than N1, the angle of refraction is greater than angle of incidence, and the refracted ray is said to move away from normal. You have studied in class 12 so these rules. If the angle of incidence theta 1 is further increased, the angle of theta 2 also increases in accordance to Snell law. Okay. And at a particular angle of incidence, the angle of refraction becomes 90 degrees and refracted ray grazes along the medium. If theta says 90 degrees, it will grazes along the medium 2. Okay. So angle of incidence is called critical angle of medium 2 with respect to medium 1. So this means that same optically denser medium may have different critical angles with respect to different optically rarer medium. If theta 1 is increased beyond the critical angle, there exists no refracted ray and the incident light is then reflected back into the same medium. Okay, so this phenomena is known as your TIR, that is your total internal reflection. So yeah, the two vital conditions or the phenomena required for this total internal reflection is: number one, the medium from which the light is incident must be optically denser than the medium to which it is incident. And the second one, the angle of incidence in the denser medium must be greater than the critical angle of the denser medium with respect to the rarer medium. Clear? So launching of light into optical fiber. Okay. So you know that light propagates inside a optical fiber by the virtue of multiple TIRs at core cladding interface. The refractive index of the core glass is greater than that of cladding. This means the first condition of TIR is satisfied, or we are able to meet the first condition of TIR. Okay, all the light energy that is launched into the fiber, optical fiber, through its tip does not get guided along the fiber. Only those light propagate through the fiber which are launched into fiber at such an angle that reflected ray inside the core of the optical fiber is incident on core cladding interface at an angle greater than your critical angle of the core with respect to the cladding. But before delving into the rigorous mathematical calculation, we will visualize the light energy that can be launched into the fiber. Okay, such so yeah, such planes which contain fiber axis called meridional planes, and consequently the rays lying in a meridional plane are called meridional rays. The meridional rays always remain in respective meridional planes. Fine. So yeah, you can see the diagram. It is the pictorial representation of the meridional ray representation. Launching of meridional rays. See the diagram clearly. You will understand the entire theory too. There are there may be infinite number of the planes that passes through the axis of the fiber, and consequently there are infinite number of meridional planes. This indirectly indicates that there are infinite number of meridional rays too, which are incident on the tip of the fiber, making an angle with the fiber axis as shown in above figure. These meridional rays, which get totally internally reflected at core cladding boundary, meet again at the axis of optical fiber as shown in figure 3.5, which will be shown in below. Okay, in the next slide I mean to say. In the figure, the meridional plane is the plane of paper which passes through the axis of fiber, and the incident rays, refracted rays, and the reflected rays lies on the plane of paper. Though only two rays are shown in the figure, for the sake of clarity in practice, there would be a bunch of rays. Okay, there can be bunch of rays which are convergent at the same point. So meridional rays are classified into two categories: bound and unbound rays. Fine. The rays which undergo TIR inside the fiber core remain inside the core at all time along the propagation, so they are called bound rays. The rays which fail to undergo the TIR inside the core are lost into cladding and are called unbound rays. The dotted rays which is shown in figure 3.2 are your unbound meridional rays. Since all the reflected rays meet at same point, a region of high optical intensity. Listen, if all the rays are concentrated at same point, they will automatically your high intensity. No, it will be high intensity, isn't it? Since these rays undergoes the multiple TIR at core cladding boundaries, they meet repeatedly at axis at regular interval along the fiber. This called multiple region of maximum intensity along the axis of fiber. Also, the set incident ray would have different angle of reflection at core cladding boundary, and consequently have different points of maximum intensity along the fiber axis. Thus, it can be visualized easily that at output end of the optical fiber, the maximum intensity will be in the axial region of the fiber core, and intensity would gradually increase as they move away from the axis toward the periphery of the core. Okay. So please go through this 3.5 diagram. I have explained you in theory also, but for your more clarification, you go through it. Now I will move to the next slide. Another way of launching a light ray into the optical fiber is to launch it in such a way that it should not lie in a meridional plane. Okay, these rays are called skew rays. These rays are called skew rays. Pictorial representation, you can see there are launching of skew rays. Okay, so I will explain this entire diagram in theory in a better manner. So skew rays propagate without passing through the central axis of fiber. In fact, the skew rays goes on spiraling around the axis of optical fiber. The light energy carried by them is effectively confined to an annular region around the axis as shown in figure 3.6. Consequently, at output, skew rays will have minimum energy at the axis of optical fiber, and it will gradually increase towards the periphery of the core. Okay, I have also mentioned you earlier that it will increase towards the periphery of core. Thus, when the light is launched into an optical fiber, there arises two possible energy distribution. One which has maximum intensity at the axis due to meridional rays, and other which has minimum intensity of at the axis due to which will have the minimum intensity at the axis due to your skew rays. Okay, skew rays will correlate to your minimum intensity. Okay, so thus on the whole, there are two ways of launching light in an optical fiber. Two ways of launching light in an optical way. Number one, the light can be launched either as meridional or skew rays. Assuming light to be launched in meridional rays into optical fiber, let us carry out the simple analysis. For that, let us concentrate on figure 3.7 below. Okay, so you will concentrate, and there you will find this red highlighted data. So I will show you the figure then. So yeah, so if I come, yeah, the ray CO is launched in the fiber at an angle alpha. That its refracted ray is incident at the core cladding boundary at its critical angle theta c. If light ray is launched at an angle more than alpha, then refracted ray just reflect out to the cladding, because the angle of incident of its refracted ray at the core cladding interface is less than your critical angle. Thus, the angle alpha is indicative of maximum possible angle of launching of a light ray that is accepted by a fiber. Consequently, the angle alpha is the angle of acceptance of fiber core. Okay, so you know that alpha, when this alpha, that is the acceptance angle, will form a conical shape, isn't it? I will show you in the diagram, but just for the understanding purpose, it will form your conical shape. This cone, it will form a cone, and this cone is called acceptance cone of fiber. Okay, let me show you the figure. Yeah, are you able to see this cone? It is the acceptance angle of the cone, acceptance cone. Okay, refer it diagram, you will understand the entire theory which I told you. Here AO is incident ray at an angle alpha, and CO is incident ray at an angle alpha, and AO is incident ray at an angle phi. Okay, BO is incident ray. Okay, COC is acceptance cone. An optical fiber. Numerical aperture. Okay, as I have mentioned, I have told you about acceptance angle. So the reflected ray for the incident angle in the cone is incident at core cladding interface at an angle theta c, which is your critical angle of the core with respect to the cladding. The angle of refraction for critical angle of incidence of 90 degree, and the refractive ray thus will graze along the core cladding boundary along BC as shown in figure. Okay, according to Snell law, the incident and the reflected ray lie in the same meridional plane, which is the same plane of paper in this case. Okay, so you can see the diagram. We will apply here the Snell law. So after applying Snell law, we will get we will in the diagram we come to know that your angle theta is 90 degree minus your critical angle, that is theta c. So from there you will get sine alpha, and sine alpha is n1 by n cos theta c, where cos theta is c. By using trigonometry, we will get under root 1 minus sine square theta c. Sine theta c is n2 by n1, so cos theta will be obviously 1 minus n2 by n1 whole square under root. Okay, sine alpha. Okay, sine alpha will be in a more simplified manner, it will become under root n1 square minus n2 square by n. But here n will be 1 because light is launched in air, and air has refractive index 1. You can see the greater the value of alpha, more is the light accepted by the optical fiber. Okay, and A is your sine alpha. So greater the value of greater the value of Na, more will be the collecting efficiency of optical fiber, and better more the value of Na means better is your fiber. So it the so and so for the greater value of Na, the first condition is for maximizing difference, either refractive index of core N1 has to be increased, or the refractive index of cladding N2 has to be reduced. Okay, so you can read this entire article. So your bandwidth is I will talk about the bandwidth. The pulse of light, which might originally to be of width t second, then now might be of t plus delta t seconds. The inside the fiber core. Okay, so your delta t, which is your pulse broadening, will be equal to L into N1 into N1 minus N2 upon C into N2, where N2 is your refractive index of cladding, N1 is refractive index of core, delta T is pulse broadening, and C is velocity of light in vacuum. So bandwidth, bandwidth is reciprocal of pulse broadening, that is delta T. It will be bandwidth is equal to 1 by delta T. You can read this entire theory. I will show you the diagram now. So it is also a theoretical part. So advantages of optical fiber. Optical fiber, as we have studied, that it has a greater bandwidth, it has a and faster speed, it is cheap, it is thinner and lightweight, and it has higher carrying capacity, and less it has less signal degradation, because the loss of signal in optical fiber is less than in copper wire. Okay, light signal, unlike electrical signal transmitted in copper wire, the signals from one fiber do not interfere with those of other fiber in the same fiber cable. So it means we can have a more clearer phone conversations and TV reception. Okay, so it has a longer lifespan, more than 100 years. And the disadvantages that it has, that the light emitting source are limited to low power, and it is fragile, and the distance between the transmitter and receiver should keep short, or repeaters are needed to boost your signal. Okay, how you can select the right optical fiber. So optical fiber are gaining momentum in communication networks, and that emerges a dazzling array of vendors competing to manufacture and supply the fiber. When selecting optical fiber, you had better start with reliable vendor and then consider the selection criteria. Okay, thank you and have a good day. With this, I would like to adjourn my topic. Okay.